All right, hello and welcome to Algorithms Live. This is the second episode this week. The first episode took place on Friday, and I decided to have this bonus episode with a late announcement. So for people that are watching, as a surprise episode. And I really making up for the few weeks ago when I had to unexpectedly cancel the episode, had trouble scheduling it. But I thought these two topics like meld really well together. They're a little bit simpler. Topological sort isn't really an advanced algorithm, but it ties really nicely to this other method for strongly connected components. And so I kind of want to link the two together and just talk about these ideas. And so I'll be showing quite a bit of code, coding a few things, talking about how these things relate. And none of the ideas will be that complicated, but I think at the end of this, you'll really understand how these things work. Okay, so I want to start off with, there's two, I guess start off with like how topological sort works and what problem we're trying to solve here. So the classic example of what topological sort is doing is imagine you have some classes that you need to take, maybe at a university, something like that. And you know that certain classes are prereqs to other classes. So we've got these kind of classes like this. Maybe class 6 comes after class 1, and so on. You draw a directed edge when one class comes after the other. And the idea is, for this formulation of the problem, you can only take one class every semester. And you want to take classes that are prereqs before you take the actual class. So it's a little bit simplified problem in that way. And so you're trying to construct an ordering on these vertices. That have that property. So I can look at two of the vertices. I know that 6 has to come after 1, or I know that 5 has to come after 1. So if you took whatever the topological ordering is, and you end up drawing the edge, it should go to the right in the topological ordering. It's just part of the definition here, if we go from left to right labeling these things. A thing to notice about this problem is the topological ordering can be any order that works. So in this case, 1 and 2, I could actually process 2 before 1. So there's this kind of cool problem that you could come up with. It's like, given top ordering of a graph, one is find the topological ordering, but there's another one where it's count the number of orderings. And that's actually a pretty hard problem. And so we typically say that problem is sharp p hard. So there's this special complexity class called sharp p, has to deal with counting problems. So this is an example of a sharp p hard problem, is count the number of topological sorts. Another example of one of those problems would be count the number of bipartite matchings. So that would be another sharp p hard problem. So it's a really neat complexity class to go read about if you're into complexity theory. But getting back on topic, this is the problem we'd like to solve, and I'm just going to show you two algorithms that will solve it. And this first one is called Kahn's algorithm, and it's relatively simple. And so here's the idea. So I'll do a slightly different graph this time. So I have node 1, goes to 2, goes to 3, goes to 2, goes to 4, something like that. And so here's the idea. What we do, and maybe I'll add node 7 in here, something like that. Okay, so what we do is we start looking at what's called the in degree of the nodes. So in degree of some node is the count of the edges coming into it. So I look at a node like node 3, you can see there are 2 arrows coming in. So its in degree is 2. So there's 2 edges coming in. And what we care about is we care about nodes that have 0 as their in degree, such as node 7 or node 1. And so this is where we get our choice. At this stage in the topological sort, we can pick either of these nodes without consequence. So what I'll do is I'll pick node 1 initially, and I'll make that the first part of the topological sort. Now, so the idea with Kahn's algorithm now is I just remove this node. And it's gone, and remove the subsequent edges. And now I have a whole new graph. And I guess kind of inductively, I run top sort on this. And so in this case, I have 7 has in degree 0. So I can take 7, remove that edge. So now I'm left with 3 is the only node with in degree 0. So I'll take 3, remove that node from the graph, and just continue on my search that way. I look at node 2. Node 2 has in degree 0, remove it from the graph. I see node 4. Node 4 has in degree 0, remove that from the graph. Node 5, and then node 6. So that's Kahn's algorithm. That's pretty much all you do. But you can implement this in V plus E time in kind of a smart way. So I'll be going over implementation details in a second. So that's the first way to run it on a graph like this. I'm going to go again. I want to show you what happens when we end up getting a cycle in the graph. So what I'll do is I will add a cycle in the middle here. Maybe not that big. And so what could happen is I could have in degree 0 nodes. So I'll remove them from the graph, and that will be part of my top sort. But if it gets stuck, in other words, you have to be a directed acyclic graph to not have a top sort, or to have a top sort. We talked about DAGs in the SCC video. So I removed that from the graph, and you'll notice that nothing has in degree 0. So if we end up stuck, if we ever don't process all the nodes, then we know the graph has a cycle and it's not a DAG. If we run a top sort successfully, then the graph is a DAG. So this doubles as a cycle detection algorithm. You can find if the graph has a cycle just by running Kahn's algorithm, pulling off these nodes from the sources, and end up getting a graph looking like this. So I'm actually going to go code this one. Just to show the implementation details and kind of how this looks. And then we'll test it on some small graphs. All right. So I've got these fancy new templates I'm going to play around with. So I'll call this top sort. Something like that. Pick a graph class. I think I'll be using this later, so might as well build one now. And showing off my poor coding style when I'm trying to be fast, but that's okay. That's my graph. So I'm just going to use standard graph stuff. So the file is going to be number of nodes, number of edges. Just so I don't confuse things, maybe I'll do graph G equals new graph. Okay. I'll use this code for all 3 pieces of code I will write today. So something like that. Okay, so let's start talking about how this top sort works code-wise. So what I'm going to do is I'm just going to make a table for in degree that's going to be helpful when writing the top sort. And then I need to loop through all my edges. I can do them while I'm reading in the graph here. So every time I'm making an edge, node j's in degree is going up by 1. You can also save information on the out degree here if I really wanted to. I'm just not doing that because I don't need it. Okay, so to get this top sort to work, I do something very similar to a breadth first search. So I'm just going to make a queue, and I just loop through all the nodes. And if I see something that has in degree 0, then I add it to my queue. So that populates things. So I get all the nodes that could come next in the queue right away. And then while I still have nodes in the queue, I take one out. And then I have to remove it from the graph. So this is the remove it from the graph part of the algorithm. So I just look at everything I'm adjacent to, and I say that you've lost an edge. And so the only thing that can tend to 0 now is the nodes I've touched. So if I end up getting something with in degree 0, then I add it to my queue. And if I want to print out the top sort as I go, I'll do that here. I actually use a string builder. Maybe this is how I typically do it. And so what you'll want to do is maybe if you get to the case where you don't hit all the nodes, you could do a cycle detection. But the way I'm going to write this code here is I'm just going to assume that I always get all the nodes. So I'm given a DAG. But it can vary. Okay, and that's all there is to the top sort algorithm. So pretty short, pretty simple. So I want to add a few things. I have some sample graphs here. So I have like a 6, 7. So 1 goes to 2, 2 goes to 3, 1 goes to 3. Something like that, and that will be my second graph. So I'll draw these out in a minute and kind of show you what's going on. But they should work as just samples to go read. I should print them out with a +1 here. So 1, 2, 3, 4, 5, 6 is actually correct. And then 1, 6, 5, 4, 3 is also correct. So you could draw out these graphs yourself and kind of just see how they're working. But they're pretty simple looking. I do want to comment on one last thing. One of the things that makes this algorithm really good compared to the second one you'll see is you can also get out the lexigraphically first topological order just by changing the queue to be a priority queue. So it slows down the algorithm by a log-n factor. But then you do get the power of the lexicographically first. And that's all I change about this. In Java, the functions end up being exactly the same. So I'll write that here. And you'll see this is actually lexicographically before this one. So if the problem is asking get the lexicographically first top sort, this is the algorithm you want to use because it's a lot simpler. Okay, so I want to go back to board here. I want to start talking about a second algorithm, and that's this Dfs top sort. And the reason we're talking about this is a really good precursor to Kosaraju. And that's the whole reason I bring this one up. So it works a little bit differently. So I can code it here. So this is actually T2. I'm drawing it out right now. So if you're wondering what the top sort or the graph for the top sort is that I was drawing, this is the graph. Something like that. Okay, so the idea with this one is what we're going to do is we're going to run a normal DFS. And so I go to node 1, I pick some way to go. So I can go out to node 5, and maybe go out to node 3. And I'm going to do a few kind of weird things. The first thing I'm going to do is when I'm visiting a node, I'm going to keep track on whether or not it's on my stack currently, so my call stack. So if I'm at node 3, on my call stack, there's 1 and 5, just looping back. And then when I'm done processing the node, I'm just going to mark the node as done. So basically, in terms of low linking, it's going to be a way of detecting back edges versus cross edges. So cross edges are absolutely fine when you're doing a DFS on a DAG, but if you have any back edges, then you have a cycle. So it's a really nice cycle detection algorithm. If you ever, all you have to do is, in terms of our low linking process, if we think of DFS low link, if you detect the back edge, then you know you have a cycle. So you have, basically, you just need 3 different states. You need, I haven't seen this node yet. This node is currently on the call stack, or I've already processed this node. And so I'll be going down here. I'll be doing my DFS like this, get out to 3, nothing is found, come back to 5, nothing is found. So I come back here, continue on to 6, and then you see I get this cross edge. So maybe I mark that in blue. Six goes to 3, but that's not in my tree. Go out to 4, everything's looking fine. Come back up. It seems I've missed a cross edge. So 1, 2, 3, 4. Yeah. Oh. And then I do a second DFS. So one of the neat things about DFS is you might not hit everything. So you just find some other nodes to start DFSing from. And then this is also a cross edge. So this one goes to 5. Something like that. So that's an example of a cross edge. And so our algorithm was fine here. Let's talk about the modification. So as I'm running my DFS, what I'm going to do is, as I finish processing a node, I'm going to push it onto a stack. I guess I didn't explain that piece of the algorithm very well. So let's say I have a stack like this. We'll go back here, start running our DFS again. So the idea is I start at node 1. I go to node 5. I go to node 3. And then 3 is done being processed. There's nothing adjacent to 3, so I put it onto a stack. So then I backtrack to node 5. 5 has nothing left to go to, so I also put 5 onto the stack. And then I move out to node 6. And then I get my cross edge. But I also move out to node 4. Done processing node 4, so I put that onto the stack. Done processing node 6, put that onto the stack. And then done processing node 1, put that onto the stack. Get to node 2, I get another cross edge. And then I'm done. And so now if I pop these things off the stack in order as I'm done with my algorithm, and you might wonder where node 2 went. Oops, forgot to put it on the stack. There we go. And that's my topological order. So you might think about why. Why does this work? So think about this. When I'm done processing this node, I've already finished processing its entire subtree. That subtree is everything that I can reach, or it was handled previously if it's a cross edge. So if I'm out at node 6, I've done processing everything else on the cross edge, or I'm done processing this edge. So 2 important cases. If it's a cross edge, everything down that subtree will have already been pushed onto the stack. If it's a normal edge, everything in that subtree, if I push it onto the stack when I'm done processing, will already be pushed onto that stack. So everything that is on after me in terms of what I can reach will come after me in the top ordering. And so you have 3, 5, 4, all that. So this is the right time to insert myself into the topological order because I'm not causing any edge to go from right to left to a previous thing. So that's basically the idea with the ordering, and keeping the 3 separate states on whether or not you've hit something is just to detect back edges in terms of the top sort. Okay, so it should be pretty easy to see what happens when you have a cycle. So I'll do that very briefly. We'll just do a nice simple one, something like this. So I start from node 1. Go out to node, I guess this should be node 2. Go out to node 2, go out to node 3, go out to node 4, and then 4 goes back to 2, and that's our cycle. So the series of forward edges down and the 1 back edge will form our cycle. So you always detect cycles that way, and those are the only ways you can get a cycle in a top sort. So you'll just flag these things as you're coming down on the stack as being on the call stack, and then as you're leaving the node, when you push it onto the top sort stack, you change its state to be, I'm completely done with that node. Okay, so I'm going to go code this one. So you get an idea of how this works. All right. I'll read in the graph. Don't have to do anything here, and I'll just delete all the code from the previous iteration. I need some kind of stack, so I'll put that here. I use arraydex for everything. All right, so DFS time. I also need a state array. I'll call it a state array. And so the state array, it'll be 0, unmarked. 1 is on stack, and call stack, I should say. And 2 is done forever. These are my 3 states. So I'm going to do state like this. That should be all zeros to start off. And then I just loop through all my nodes. And we just do a DFS on that node. So this part right here is cross-edge case. So if we ever get to a state and it's already in this form, then we're done with it. Otherwise, you could have a back edge. And then so you want to return it as a cycle. So I'll do the cycle detection style. So I'll add a Boolean array. I'll do that kind of DFS. So if it ends up having cycle, it returns true. So this is the cycle detection case. So this is the back edge case in terms of my low linking. I don't have a cycle yet. I'll do it that way. Suppose I should move my graph up here since I'll be using it. That works. And I can run a DFS. So I need to do a few things. The first thing is I'm at node I and it's currently unvisited. So I'll mark it as being on the call stack because I'm currently now on the call stack when I hit this stage. Then I explore every other node in the tree, normal DFS style. And if I end up detecting a back edge somewhere down that DFS, then I just return true. I found a cycle. I want to get out of here. Otherwise, I haven't found a cycle yet, so I keep doing my search. And then the thing here is on the post order side, this is when I set my state to be 2 because I'm done processing it. But this is also where I push this node onto the stack, and I end up getting my ordering this way. So just do a DFS in that style. And then we could just say something like not DAG. Return. Then I could do my top ordering. Probably add 1 to it because everything's 0 indexed. And so that's how you do the second form of top sort. Which appears to be correct, I hope. Yeah, take a look at T2 real quick. So 2, 1, 6, 4, 5, 3. And that appears to not have any conflicts with my graph that I was drawing before. Okay, so that's the second form of top sort. So how does this help us for Kosaraju? talk about, so now we're going to talk about Kosaraju's algorithm. Okay, so let's take a look at a graph that has a strongly connected component in it that's bigger than size 1. Maybe I'll flip an edge here, and maybe I'll flip an edge here. So you can kind of handle these by hand. This is an SCC. This is an SCC. This is an SCC. And this is an SCC. And one of the things you'll notice if I just did a DFS, like if I just started somewhere in this component and did a DFS, this is the sync node, has out degree 0 in my metagraph, then I would hit everything in the SCC and only the things in the SCC, just through a normal DFS with no extra work at all. Same thing here. So let's say I mark all those nodes. Let's say I do all that work, I mark all those nodes. So these nodes are all marked. Then what I could do is the graph I'm left with, let's just delete everything. If I started somewhere in this SCC, then I would only hit things in my SCC, and then I'd be done. And I could mark all these nodes as being done and pull those out as the SCC in my metagraph, erase them. And then these are the only nodes that are left in my SCC. So I can just hit all of them if I did a DFS, normal old DFS, nothing special. Pull that SCC out, and same thing with this last piece. And that's all I'd have to do for that algorithm. If I had a nice way of finding the topological ordering of my DFS, of my strongly connected components, like if I could just find nodes in that order, so in other words, do a DFS, get the ordering on this graph, then everything would be set. So the problem is topological sort doesn't work on my DFS algorithm because the graph has cycles. So we're going to make a second observation. Here's observation number 2. If you take a graph and you transform it to get something called the reverse graph. So the reverse graph, if there's an edge from I to j, you add the edge from j to I. So I'll just do these in reverse. The important thing to realize is the SCCs are exactly the same. Because remember, the definition of SCC is that I has to get to j, and j has to get to I. So if you reverse the graph, this property stays true. And then anything whereas only I could get to j, now j could only get to I. And if there was something that j got to I, then only I could get to j. So it's very easy to prove that relation is true on the reverse. So our strongly connected components are exactly the same. Okay, so here's the idea with Kosaraju's algorithm. We're going to run a DFS first, and let's just think about how this looks. So I'm going to draw out another graph and put these two observations together. something like that. Something like that. Maybe it's a 9. Okay. So 1 goes to 2 goes to 3. And so I should be putting things on a stack, but oh well. 3 goes to 4, goes to 9, goes to 7. It's a really deep DFS. Goes to 8, goes to 6. And so 6 is done, so 6 goes onto the stack. And then I go to 8. 8 is done, 8 goes onto a stack. 7 is done, 7 goes onto the stack. So I guess I should be crossing these out as I'm going through them. 9 goes onto the stack. 4 goes onto the stack. 3 goes onto the stack. Oh, wait, no, 3 doesn't go on yet. You have to process node 5. 5 goes onto the stack because it's already done. Then process node 3. 3 goes onto the stack. Then followed by 2, then followed by 1. So we will pop these off. And if you recall, in this order, so what I'm going to do is, it's not always the case. So the thing that you're going to look at here in this algorithm is it's not always the case that if you have an edge, it's going to point to the right, because this graph has cycles. What we've basically done is we've done the DFS topological sort procedure. And we have cycles here. They form backwards in this graph. But one of the things that you'll notice is these nodes, the root of the SCC in terms of like what gets processed first. So we'll call this the root of the SCC. If you're running from left to right, you'll hit the first node you hit in that SCC will get processed first. And anything that it can reach will have come later in the graph in terms of what you pull out in the stack. So it's going to be a forward edge to anything that comes later because we did a DFS. It's going to be a forward edge here. So 1 is going to reach everything that this SCC can reach, right? So if you look at the reverse graph, then the root node of the SCC, whatever that root node of the SCC is, that's the thing that's going to get processed first. It's going to be a sink in terms of our graph. So if I take this original graph, so let's erase things. I'm just going to build the reverse graph. So reverse all the edges. Or something like that. Then I'll start my DFS from here in terms of that ordering, and everything that I hit will be in the SCC. We're just going to pull that out. Then I'll try 4. So I'll hit these next few nodes. Those are all processed. I'll try node 5. So I get out to node 5. It can't hit anything else. So I just do a DFS procedure, see what I find. That's an SCC. Then I look at node 4, see what it can hit. Can't hit anything else. So I process it. That's done from my algorithm. I'm going to move this up. I get out to node 9. I think, okay, what can I hit from node 9? Only this node. So it ends up getting processed. It's in its own SEC. Then I process node 7. So 7 can hit here, gets to 6, gets to 8. That's all part of one SEC. So I process them all together. And the thing you'll notice is the order that I found these. So 1, 2, 3, 4, 5. That is the topological order of my metagraph, of the original metagraph. It's reverse topological order of the reversed metagraph, or reverse graph. So what you can first run the DFS style topological sort detection algorithm, it's topological sort finding algorithm. And the order that you find those nodes is going to be in a good order on the metagraph as well. And then you just process it in this reverse graph kind of way. You can pull out the topological order as we go. Okay, so I'm just going to code this one. So a lot of the code's going to be the same. I'm actually going to leave off this and just use a scene array. So in this version, I don't need to detect if there's a cycle. So I can remove this state entirely. And if it's seen, I can just return. What I'll do is I'll take in my graph and I'll run a DFS. And I'll just work from there. So the code's going to be the exact same as that top sort. I can just run it like that. Okay, so what I'll do is I run my DFS. I get everything on the stack in the order I want to process it. And then I kind of want the reverse graph. So what I typically do when I write this code is I make a reverse function as part of my graph class. This is why I have a graph class. So I just make a new graph called reverse graph, make it size n. I loop through all the nodes. I loop through all the edges of those nodes. And I just add the nodes in reverse. Just a little helper function. Now what I do is do this, and I can basically do whatever algorithm I want. So I'm going to do a DFS again, but I'm going to do a BFS. So I can also pull out strongly connected component IDs this way. So what I'll do. Now I just run a BFS from this position. And it's on the reverse graph. Now I'll take it out this way. Right. That's all I do here. You could also replace this with the DFS. Some people just do 2 DFSs, and that could work equally well. But right now, all I'm doing is I'm using IDs as a visited array, and I'm just marking the strongly connected component ID as I'm finding them. And it's fairly easy to just code this way. I should change the way my scene array works. Oh, it's K1. So all I'm going to do is I'm just going to make a really simple graph. I think I'll do 8 nodes and 10 edges. So 1 to 2, 2 to 3, 3 to 1, 3 to 5, 3 to 4, 4 to 6, 5 to 6, and then 6 to 8, 6 to 7, and 7 to 8, something like that. Well, maybe I'll do 8 to 7. Should give me a few strongly connected components. Appears not to be working, so maybe I messed up something. 6 to 8, 8 to 7. Wait, yeah, maybe I'll just reverse this. Nope, that's perfectly fine. Cool. So these are strongly connected components found that way. So that's all there is to Kosaraju. It's a lot of people like this one as opposed to Tarjan just because it's a little simpler. You're looking at a DFS here that's pretty simple, and all it's doing is just that topological sort, except it's not really finding a topological sort. It's just finding something with those properties, with those reachability properties. And then if I process them in reverse order in that way, then on the reverse graph, I'm just going to end up processing the root of each strongly connected component in topological order of the metagraph, which is just really nice. And so I'm doing a normal reachability test here. This is very similar to regular component finding. If you just have an undirected graph, can you find components? And that's all I'm doing here. Yes, and so Kosaraju's is the one with 2 DFSs. So I guess the only change here is I'm using a BFS for the second piece. But you could easily just change this to a DFS. Yeah, and you can print out things like this. So thanks for watching, everyone. I hope you all enjoyed this episode. The next episode is going to be on Wednesday. I'm thinking of doing some stuff with sparse tables as they relate to LCA, because I think that algorithm's kind of neat. And so the next episode will be on a Wednesday instead of a Friday, just to handle some logistical issues. But I hope you all enjoyed this, and I'll see you all on Wednesday.